Hi everyone, my name is Jim Shepik, and today I'm going to be presenting to you a project where I used reinforcement learning to play a game called Punish. Punish is a fast-paced card dueling game created by my best friend Houston Webb, who is the creator and owner of Happy Slaying Studios, which is an up-and-coming indie game studio. There are a lot of different ways to play Punish that we've experimented with in its development process, but the standard game is, to put it in game theory terms, it's a two-player simultaneous play game of incomplete information that is extensive, so it occurs over multiple turns. Houston is sort of working towards a Kickstarter release, so if this project interests you, please anticipate that. Go to his website, Happy Slaying, for updates. Check out itch.io, which is where the virtual distribution of the game is hosted. All right, a crash course of the rules is this. Both players draw a hand of 5 out of a deck of 15 cards. You can see the cards on the right of this slide. There are 3 copies of each card, and then 3 cards are turned face up in the discard pile to give players a little bit of extra information. 2 cards stay hidden in the deck. Players have 3 hit points, and the goal is to reduce the opponent to 0 hit points before they do that to you. The game is played through measures, which is kind of a fancy way of saying rounds. Each measure consists of 4 breaths in which actions are taken. And after a measure, players can heal 1 HP if they were damaged, and the cards get reshuffled and redealt. Every breath, players reveal their cards at the same time, and the effects are resolved in terms of priority, which is indicated in the top left of the cards. Smaller numbers happen first. In the bottom right of cards, you can see swords indicate how much damage a card does. Shields indicate how much damage a card prevents. And then in the top right of the punish card, there's a little ZZZ, which means that you are exhausted for your next breath, so you can only take the rest action. If both players play an attack of the same type, then the attacks clash and nobody takes any damage. Additionally, if you don't have any good options in your hand, you can feint once per measure, where you discard a card and take one of the 2 cards that are hidden in the deck and use that as your play. I know that explanation was a lot to take in at once, so maybe it'll help if you see the game in action. Here, I'm going to play against the champion PAWNN agent, which is the highest performing agent that I produced in this project, so take a look. I have a pretty good mix of offensive and defensive options in this hand, and that means that the opponent does too. I'm going to guess that it's going to try to play defensive, so I'm going to call it out and try to hit it with a little rush, hoping that it's going to play a dodge. Guard. No damage. Well, maybe I'll guard. Another guard. The opponent's playing it very safe. What if I were to dodge? Dodge. Man, this thing is anticipating my every move. Punish. And it clashed. No damage. All right. I'm going to play it a little bit more dangerous here. I'm going to start out with a strike. Guard. But it still took 1 damage. Strike again. Dodge. No damage. All right, dodge. Ooh, I dodged the punish. The AI is exhausted now, which means that I get to use my punish and it just has to sit there and lose. I win. For those of you who don't know what a Markov decision process is, imagine a network of interconnected game states. You transition between states semi-randomly based on, certain probabilities like shuffling and whatnot, as well as on which action you take. We also treat the enemy as part of the environment, so the enemy's strategy, or the probability distribution over the enemy's actions, is part of how the overall transition probabilities are calculated. We made a couple of assumptions for this model. First, we ignore the measure number, because if we included that in the game state, the state space would technically be infinite because the game can go on for any number of measures. We also ignored the order of the cards that were played. That information is there, but we hypothesized that it wouldn't be super helpful and it just expands the game space, so we got rid of it. Additionally, as you play Punish, you're able to make some deductions about what's in the enemy's hand. We figured that kind of logic would emerge through the calculation of transition probabilities, so we decided not to include it in the game state itself, just to have a small game state space that we can that we can train over. With these assumptions, game states have 18 features: the breath number, the quantities of each card in your hand, your own HP, exhaustion, and faint status, the enemy's HP, hand size, exhaustion, and faint status, and the quantity of every card in the discard pile. Actions, you can play any card in hand. You can also faint with any card in hand. And then we encoded states and actions as integers just to make storage a little bit more efficient. And each digit was based on one of these features. This slide shows an example of some states and actions that are encoded, how we've encoded them. I encourage you to pause and take a look and see if you can understand what's going on here. Up until now, we've laid the groundwork for how we're going to represent punish in a way that an artificial agent can learn it. We talked about how enemy strategies are treated as environmental factors when calculating transition probabilities, but how exactly do we come up with those enemy strategies? Well, one option is to make this naive assumption that an enemy is equally likely to take any available action. Basically, that the enemy is just going to pick a card at random, randomly decide whether or not to feint. That might not be the best assumption, so one alternative that we proposed is the PARLESS technique: possible actions reweighted with limited empirical strategic samples. I'm a sucker for acronyms. That was a bit of a mouthful, but it basically just means using real game data to do Bayesian reweighting of naive enemy strategies. We start out with Dirichlet priors and use a total of 3 pseudo counts, which we divide evenly among the actions, which basically just means that we assume that the naive assumption is worth about 3 observations. Then we go through our data set and we pick a state. We look at all the actions that were used and we add these real empirical counts to the pseudo counts and normalize to get our PARLESS posterior. This whole process used data from 667 games. We only got less than 1% of the entire state space represented, and 500 of the games were my own, so working with very limited data here. Additionally, I made 2 models, one that used all the data, and then one that only used state action pairs that resulted in winning the game. Just to see that, maybe winners do things a little bit differently than people who aren't paying attention, and those are the people that we want to really train to beat. If you're still feeling a little confused, you wouldn't be alone, so let's work an example of PARLESS reweighting together. Consider this state. It's a starting breath. You have no guards, 1 of everything else, and 2 punishes in hand. So to compute the naive Dirichlet prior, there are 4 different card types in hand, and you can feint with each one, so there are a total of 8 possible actions. Each possible action with the naive assumption has a probability of 1/8, and that assumption for each one is worth about 3/8 of a single observation. In our data set, we only have 1 observation for this state, and in this example, the player played punish. So we add that 1 empirical count to punish's 3/8 pseudo count, and it has a total of 11/8. Everything else still has 3/8. The normalizer is the total number of pseudo counts plus empirical counts, so 4. So we go through and divide everything by 4. Punish now has a probability of 11/30 seconds, which is about 34%, and all of the other actions have 3/30 seconds, which is about 10%. So what happened here is that the probability of playing punish on breath 1 in this state has increased quite a bit from the naive baseline, which is like 12%. And that's reasonable. That's how people play punish. There's always that threat of, somebody playing punish on breath 1. It's the name of the game. The weakness of the PARLESS technique is that it only lets us reweight strategies for the small handful of states that we've actually seen. I decided to take things a step further with a technique that I call PAWNN, PARLESS augmented with neural networks. Basically, I trained a neural network to predict the PARLESS strategy distributions from game state features. There are a couple dangers that I anticipated. First, because there are so few observations for any given state in our data set, It's possible that the PARLESS strategies are really wacky or unreliable. And then the other is that there might be some problems in trying to extrapolate based on 0.6% of the state space. But I figured it was worth the investigation. I ran a lot of experiments trying to find the best neural network model for the PAWNN technique, and you can read all about it in my log notebook or my report. But the gist is that the best results happened when I trained on MSE loss, used an architecture with 18 input nodes to a hidden layer of 36, then 24, then 16, then 11, and then finally softmax activation at the output layer. I used ReLU activation in all the hidden layers, optimized with Atom, and then saw some really good results when I included a 50% chance of dropouts in the first hidden layer. Here are the validations for the final model we ended up using for the PAWNN technique. As you can see, the train and the test curves have pretty much converged, which is a really good sign about this model's ability to extrapolate to new states. In this slide, I've included a couple examples of ground truth PARLESS distributions and how they compare to the PAWNN predictions, and I encourage you to pause this slide and take a look for yourself. But I've noticed two major trends. First is that any extremely high probabilities tend to get turned down a little bit by PAWNN, which probably means that our PARLESS priors were kind of weak. And then whenever punish is available, its probability tends to increase a little bit, which kind of agrees with what we know about how people play the game. Now I'm going to explain value iteration, which is the algorithm that was used to train the agents. In value iteration, we define two functions over the state space. The v function, which assigns values to being in a state, and the q function, which assigns values to taking an action from a state. We initialize the v function such that normal states map to 0, the win state maps to +1, and the lose state maps to -1. Based on the v function, we now can update the q function. The update rule for the q function has two terms. The first term is the immediate rewards, which is basically the probability of immediately winning minus the probability of immediately losing when you take the action. The other term is the future value term, which is a sum of the v function values of all the possible successors multiplied by the probability of transitioning to them when you take the action. The future value term is scaled down by a parameter called the discount. This gives some priority to immediate rewards to prevent the algorithm from training an agent to extend the game forever. I used a discount parameter of 0.9 and that appeared to work pretty well. Once we've updated the q function for every state in action, now we can update the v function based on these updated values. And this step's pretty easy. The value of a state is just equal to the q function value of the best action from that state. And at that point, we just rinse and repeat until the error converges. Here are the results of the value iteration training. I tracked convergence by looking at how many greedy choices changed between training iterations, or how many states had a change in which action was the highest value. Interestingly, we see that the PAWNN agents converged to a much lower number of choice changes than the other models, and this might be because of the lower entropy of the enemy strategy distributions. In other words, it's possible that less randomness in the transition probabilities leads to better convergence. Here's an example of the training curves for the naive agent. You can see that the number of greedy choice changes converges after about only 50 training episodes, but it takes around 200 episodes for the RMSE to converge, which is important for future experiments if we decide to randomize over actions based on their values. Now what you've all been waiting for, the results of the playtests. Looking at this graph on the right, we can see that the champion PAWNN agent had the highest win rate by a decent margin. The next two highest win rates are human players, followed by all four of the other agents. Notably, myself and Comet, the creator of Punish, are pretty low on this list of win rates, and lower than all 5 of the artificial agents. The PAWNN models had the highest win rates of the AI, which supports the hypothesis that the agents will perform better when they anticipate human strategies, and the champion pawn agent had the best win rate, which supports the hypothesis that the AI will perform better when trained to beat winning humans, the best human strategies. Curiously, the PARLESS models actually did worse than the naive model, and I think that this was just because of inconsistencies between the naive assumptions and the small handful of empirical data. Notably, I lost to every one of these AI, but I don't feel too bad about myself because, it speaks to my skills as a machine learning scientist. And also, the bots were trained asymmetrically on my data, 501 out of the 667 games. They're kind of trained to be my arch nemesis. One shocking result in the test data, possibly the most surprising observation I made in the entire study, is that the training states are a proper subset of the testing states. In other words, every state that occurred in the training data, we visited again during the testing period. I thought that there was a SQL error on my part. I went back and checked, and this is real. I think that this means that through typical gameplay, you only see maybe a really small fraction, possibly about 1% of the entire state space, kind of like the tip of an iceberg. And what lies below is really rare, either because of, the combinatorics of shuffling or because they require, some weird gameplay, like not punishing an exhausted opponent. This heat map shows the win rates of the bots in every human AI matchup. My friends, the playtesters, really enjoyed looking at this because it's their stats. So if you're curious, you can pause the video and kind of take it all in. The conclusions we pretty much already talked about on the other slide, but it worked. The AI were able to play Punish on par with, and in some cases, better than the humans. Although the PARLESS technique didn't itself make great agents, it was critical for the pawn technique, which made the best agent. And I think the other really important conclusion of this experiment is the fact that we saw that typical play really only visits a small handful of the state space. So we don't necessarily need data over the entire state space to make effective AI for Punish. This project has been really exciting to work on, and my brain is just overflowing with ideas about what to do next. I can't wait to keep working on this project. I think some really interesting next steps would be to try to look more into this mystery of the common versus rare, tip of the iceberg beneath the surface states, and try to see what differences we can find between them. I think it'd also be interesting to look at the differences between how humans and how AI play, and to see what works and what doesn't. We should also watch how the performance of the AI kind of evolves over time as the humans learn how to beat them. Hand in hand with that, I think the next step is to really experiment with allowing the AIs to randomize over their actions instead of always taking the greedy choice in order to kind of keep the humans on their feet. Finally, I think it'd be interesting to pit the AIs against each other and see who wins out. I think it'd also be interesting to try to generate agents through other methods, like have some that take, just completely random actions, or have some that act based on hard-coded rules and see how those perform. Before I wrap up here, I've got to say thanks to Houston. Obviously, without him creating Punish, this project wouldn't be possible. But also, thank you for making all these last-minute changes to the app on my behalf so that it could generate logs and I could gather the data, and also for, frantically integrating the AI into the project before the testing period. I really appreciate it. Thank you also to all the people who contributed to the training data: Handel, Joe, Comet, Sir Jim, and Wanderer, as well as all the people who participated in the playtest: Ender, Joe, Comet, and Fish. Finally, thanks to the viewers. I really enjoyed this project. I hope you enjoyed the presentation. That's it.